All right. Yeah, thanks so much for this amazing honor. I did not expect to win this award, so it's really fantastic, I think. So I'm just going to tell you about what we've been doing with various efforts around rethinking benchmarking in AI. So these concepts of evaluation as a service and dynamic adversarial data collection will hopefully become clear as I talk. But before I talk about any of that stuff, just in case you don't know anything about me, which is probably likely with this audience, for the past decade or so, I've been very interested in this question: how do we get true human meaning into machines? So not the fake kind of meaning where we think that the computer might speak Chinese, for example, if it follows some rules in a big textbook, but the actual understanding of language that humans have. So I've been fascinated by that question. And if you work in my field, which is natural language processing, then you would think that we've made some amazing progress. So this is a plot from the DynaBench paper, actually, which was reused by Science recently, where we find that MNIST took a very long time to saturate. So this was a computer vision sort of core machine learning data set, whereas recent NLP benchmarks, things like Squad and Glue, saturated within the year. And so Glue was superseded by Superglue, which was also solved within the year. And so solving or saturation here means achieving human performance. So if you see this, that makes you think that we are kind of there, that we've basically solved natural language understanding and natural language generation. And so there even have been people at places like Google where this very famous now engineer claimed that AI is sentient. But if you actually work in the field and if you're a serious researcher, then I think you would say that there's no way that we have solved any of this stuff yet. So while the progress on benchmarks has been remarkable, we are definitely not yet done. So kind of according to this dichotomy, that then implies that we have a measurement problem. And I think we have a fairly serious measurement problem in the field of AI right now, and that requires some radical rethinking of what we are trying to do. In other words, there is something rotten in the state of the art, to borrow a phrase from Shakespeare, and this realization initially led to this paper, Adversarial NLI, a new benchmark for natural language understanding, where we tried out a lot of these ideas that later kind of materialized into the platform that we call DynaBench. So this really set me off on this journey. So it kind of is born out of frustration. So just so that you understand where that frustration is coming from, I'm first going to tell you about the problems that we have in AI evaluation. And then I'll briefly tell you about two solutions that we've been working on. So one is DynaBench, which Peter already mentioned in the introduction, but also recent work that we've been doing at Hugging Face around trying to make evaluation and like proper evaluation much easier for people to do, in the hope that people then actually do it. So I think it's pretty fair to say that AI currently is in an evaluation crisis, but that we're almost entirely ignoring it. So if you look at all the amazing progress you read about online or that you hear about from your colleagues, it's like AI is going to take over the world. And so that might be true. But if that is true, then we need to be extremely careful with how we do AI evaluation. And unfortunately, it's not taken as seriously as like all the cool kids wanting to train up the big models with fancy new architectures and fancy new algorithms. So this is something that we have to change. And so we need to think much more carefully about the data that goes into our models and how we measure the performance of the models. And so one of the main problems, as I mentioned, is that currently most of these benchmarks are saturated and AI systems outperform humans on them, even if we know that that's not really true in the real world, right? So AI systems can make really stupid mistakes, and everybody knows that it's very easy to trick these systems. That's a problem that we need to improve. And one of the reasons that these systems might saturate is because data sets that we measure performance on contain lots of biases and annotator artifacts. And so there's a wealth of literature on this at this point in time, of papers showing that there are things wrong with basically canonical benchmarks, and lots of different things can go wrong with lots of different benchmarks. So the problem is that neural nets are especially good at picking up on these sorts of biases and artifacts. So that's something that we need to safeguard against. There's also a giant reproducibility crisis in AI at the moment, where self-reported results cannot necessarily be trusted. And one of the reasons for that is very small implementational differences. So during the training of your AI system, this could be like the learning rate or something like that. But not even only during training, even during evaluation. So during inference, if you have a very small subtle difference, for example, a different implementation of a metric, so like a blue score or something in machine translation, that may lead to wildly different results. So we really have a big problem here. And one of the problems that kind of stacks on top of the reproducibility issue is that it's not straightforward to evaluate old models on new data sets. So when there's a new data set that comes out that is actually better than all the previous work, then whoever makes that data set has to reevaluate old models, but they're not going to reevaluate all the old models. So we just lose a lot of information in the transition as we shift to better and better and newer data sets. So this is something that we should try to avoid, and we should try to have backwards compatibility for these models. There's a big problem with ease of use. So while over time, the number of data sets and the number of metrics has gone up, and unfortunately, statistical significance testing has gone down, at least in the conference EMNLP in natural language processing. And so we need to have more of these things in our papers, but it's not easier to do that. So it's just more and more work. So our teams are growing on papers and things like that. So it should be easier for people, because we believe that if you make it easy for people to follow best practices, then they will. So this is something that we have to solve because there's massive growth in AI and NLP, and this growth needs to be backed up by better tooling. There's also just some classical assumptions in AI that are possibly problematic. So there's a classic assumption, I don't know if everybody here knows anything about statistical learning theory, but if you have ever read this book or seen it in a course, Vladimir Vapnik invented statistical learning theory, and essentially the one core assumption of all machine learning, modern machine learning, and all modern AI is that we have a trained set and an unseen test set, and that they are identically distributed and independent. And so modern AI systems do not actually follow this assumption. If you look at like large language models, which are pre-trained on a large data set of a very different distribution than what we use them for, and then they're prompted to elicit a certain behavior. So this makes them hugely out of domain and out of distribution compared to the training set when they're being deployed. So this is again a measurement problem where we're essentially not really measuring the thing that we're statistically modeling with a lot of our algorithms. And to add to that is that this out of domain generalization is also exactly what we would expect from humans, and lay people when they interact with AI systems will also assume this. So, you know, maybe you and I know that AI systems have flaws and this is okay, but if somebody really doesn't know anything about AI, they will be very surprised by the mistakes that these systems make. So what we think as humans is that, okay, if it speaks language, it must be capable of strong generalization, and it must have intentionality, because this is kind of the quintessential human property, right? The ability to speak language. So if it speaks language, it must be just like me. And that, of course, as we know, is definitely not the case. We also have a single metric focus and leaderboard culture where, at least in our field, NLP, but I think broadly in AI, everybody overfits massively on these leaderboards, which are extremely limited. And they focus just on a single metric. So for things like Glue and Superglue, they actually focus just on this macro average across these different data sets, which are different sizes, which are correlated in different ways. So the aggregation is not right, and the sole focus on accuracy on a held out test set is also not the right way to measure the performance of the solution, to put it in Peter's terms, instead of the sort of accuracy of the model. And finally, going to this point as well, what we really care about when we design AI systems is can they successfully interact with humans for the task they are designed to do? And then there's this caveat that it has to be in a way that it is aligned with human expectations and that it acts in humans' best interest. So there's this nice paper from Anthropic where they try to get at this point from trying to prompt a language model to be helpful, harmless, and honest. So I think this is great when you prompt language models like that, but this is not at all what we're measuring right now, right? So there is an alignment problem with AI, but we're not measuring whether our systems are actually aligned. So these are all things that I think we need to solve. And so I've been working with my various teams over the past couple of years on trying to come up with solutions, quote unquote, for these problems. And so I'm obviously not claiming that these problems are now solved, but I think that the work that we've been doing at least takes a step in the right direction, and hopefully other people can build on top of the work we've done, and hopefully together as a community we can get to a better way of doing evaluation. Hopefully, at least I've convinced you by now that there are serious problems that we need to solve. So first, for the solution, I'm going to talk about the evaluate library that we built at Hugging Face and the evaluation on the Hub project. And so in case you haven't heard of Hugging Face, which again is entirely possible, I think, with this audience, is we are a startup on a mission to democratize good machine learning, one commit at a time. We are probably most famous for the open source transformers library. So if you want to use any state-of-the-art transformer model, then you would probably be using Hugging Face. We also have the datasets library, which is the largest repository of ready-to-use datasets, where you can just load a dataset with one line of code and work your magic on the dataset. And what we've recently done is we've built this new library called Evaluate, where it's as easy as doing pip install evaluate, import evaluate if you're in Python, and then you can just load metrics in canonical implementations in a single line of code. So in this case, we distinguish between metrics, measurements, and comparisons, where a metric is something where you have a ground truth, so essentially a distance function in some metric space. Measurements are like the mathematical idea of a measurement theory, where you have some set and you need to ascribe some numerical value to this set. And then comparisons are things where, for example, McNemar's test, where you want to compute the significance, let's say, of two measurement or metric results. And so all of this is completely open source under a very permissive license. It's the idea is just to have a standardized canonical implementation for these metrics, so that everybody is using exactly the same implementation for this metric, and that is guaranteed to lead to the same result. And we think that one of the very important things that is currently missing is much better documentation for a lot of the issues that come up with metrics. And so if you work in AI, we have this thing called model cards and data sheets, where we are trying to be very, very careful with documenting the shortcomings of models and data sets, so that if there is a bias, for example, in your data set is mostly composed of people coming from North America or something, like this is a bias that's in your data that you need to document properly, so that other people are aware of it if they decide to build on top of your data set. So very similarly, we can do exactly the same thing essentially for these metrics, where you would have a metric card for accuracy, which describes how it works, how to implement it, but also what the limitations and biases are of the accuracy metric. So accuracy, of course, doesn't really work well for unbalanced classes and things like that. So these are just things that are very important, I think, to be very upfront about. We also have these interactive widgets, where if you have a metric that you're unfamiliar with, you can just play with this table here, add new values, and then just submit it, and you'll get a live result for what the metric actually does. So again, the idea here is that we help people understand better how the metric actually functions. Then once you have an idea of maybe your own metric that you want to use, what you can do is you can push these metrics to the evaluation hub. So if you have something like my metric, you can push it to your own namespace. And so it's very simple to do this. And now anybody can load this metric. So if you come up with a new way to measure models or a new way to measure data sets, you can just push your metric to the hub and now everybody can use it. So hopefully where we're going is that as evaluation papers come out and people innovate on this, they can push their metrics and share it with the community, just like people now share data sets and open source models on the Hugging Face hub. We have an object called an evaluator, which is sort of like a trainer, if you're familiar with how that works, but then specifically focused on model evaluation, which incorporates things like computing like bootstrap confidence intervals. You can also compute throughput and efficiency statistics, so you get a much richer understanding of your model performance beyond just the accuracy score. So I think that's an exciting way to have the right level of abstraction for making things very easy for people. I should say that when we talk about measurement and things like that, we're not just talking about models. So there's also this data measurements tool from Margaret Mitchell et al. In my team, where they are trying to very carefully measure what is actually in the data set. So very often the data set itself already has lots of biases and interesting things in there that you want to be aware of before you even start training your model on it. So we have a very nice tool for trying to analyze this for any data set on the hub as well. So the idea here is that if we make it easy for people to follow best practices, then people will follow the best practices. And the question then, of course, is how easy can we actually make this? So if you take a step further from the evaluation library, you can actually make everything happen on the Hugging Face hub. So I'm going to show you in a minute what that looks like. But so this hub hosts models and data sets, and now also evaluation methods. So things like measurements and metrics and comparisons. What we would like to be able to do is automatically evaluate any model on the hub on any data set using any metric just at the click of a button. So essentially there is no code required at all for this. It's just evaluation as a service where you push your model to the hub, or you push your data set to the hub, or you push your metric to the hub, you go click, 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 and then you have some results. So you don't have to really do anything else besides that. So just very briefly under the hood, how this works is we have this data set page on the hub. There's a model evaluator, which has our auto train product at the back. This opens up a pull request on the model card. So this is the model card is the documentation of the model. Then there is a leaderboard that shows all of the results that are on all of the model cards for models on that particular data set, evaluated on that particular data set. So this is all completely free. So we just hope that it will make things better for the community. So let me just give you a live demonstration of what this looks like. So this is the Hugging Face website. We're looking at the dog food data set. So this data set contains pictures of fried chicken and muffins and dogs. So in case you didn't know, some types of dogs really look like either muffins or fried chicken. So we thought this would be a funny data set to focus on. And what I just described to you lives here in the top right. So we have this evaluate models button. And so if you go there, you go to a model evaluator space where you can configure what this looks like. So normally this is already filled for most data sets and models. In this case, just to demonstrate it, is left empty. So you can really configure a lot of the different things that you want to do. So like what split you're interested in, how you want to configure the label mapping. You can add additional metrics that you would be interested in, including community metrics like this one here at the top. And then once you've configured all of that, you can just say, okay, like I want to take, like, let's say I trained up this ResNet model here. You click evaluate and this triggers the job. And then you are in business. So you just have to then wait for the model to be done evaluating, and this will open up a PR on the model card. And once that PR, so this is a real pull request like on GitHub, once that PR is landed, then it will show up on the leaderboard here. So as you can see, this leaderboard here shows the evaluation results for this dog food data set. So the hope really is that we can work together with the community to make everything so easy that we do things the right way, sort of automatically. So very recently, we announced that we also support this for very large language models. So if you are interested in language model technology, you can evaluate up to 66 billion parameter models for free, completely for free on the hub. again, just at the click of a button, which I think is a very nice service to offer to the research community. All right, so that was the Hugging Face work that we've been doing recently. And now I'll talk a little bit about DynaBench, which is this platform for taking a step even further. So with DynaBench, we're really trying to be what I like to call a research platform for conducting a giant community-based scientific experiment. So DynaBench is supposed to be in flux and always trying to innovate in how we measure things. So moving beyond just model evaluation to data evaluation and focusing on different aspects of the many problems with AI evaluation that I outlined in the introduction of this talk. But yeah, so one way to describe it is just as an effort to challenge a lot of the current dogma that exists in the field. And so mostly focusing on AI benchmarking, of course, and we really want to help push the boundaries. So as the name suggests, DynaBench, we're trying to make all the things dynamic. And so we want to move beyond this paradigm of having static test sets that are IID and things like that towards a more dynamic future. And the best way for me to explain how this works is to use this diagram from the Adversarial NLI paper and data set. It looks very complicated, but it's actually very easy. So we'll just step through this together. So the task that we're trying to solve here is natural language inference, which means we have a piece of text, a context, and we need to have a hypothesis. So a second, like one sentence, for example. And then the goal of the model will be to predict the target label, which is either entailing or neutral or contradiction. So there are three possible labels here. And so what we do is we have these crowd workers write hypotheses based on a given context and a target label. So just a paragraph and say like, okay, you should come up with an entailing example, but their goal is to come up with an entailing example such that this model here gets it wrong. So we have a human and a model in the loop, and this model's prediction goes back to the writer. So the writer will learn whether the model was correct or not. And what we then do with the example that was created, if the model was correct, okay, it's interesting. So we'll add it to the training data. We can still use it. Maybe we want to filter out some of that training data at some point, but it's still useful information. So you don't want to throw it away. But if the model is wrong, then it's really, really useful information because you essentially just found a failure mode for your model. And you want to be able to measure whether you are making progress on this failure mode over time. And you want to be able to address the failure mode. Of course, if this is a crowd worker, then you cannot necessarily trust them. So you have to very aggressively verify all of the examples to make sure that real humans also agree. So it's not that we accept any adversarial example as a valid example. It has to be an adversarial example. So model fooling, something that the model gets wrong, but also something that other humans would agree is right. So that's very important. And if that doesn't happen, then we throw the example away. So finally, we end up with this bigger train set and a dev and test set, which are comprised mostly of these model failing examples that were verified by real humans. And once we have sufficient data here, what we can do is we can train this model on this data as well, so that we now have a strictly better model. And that's this one here, which we can then put back in the loop. So the idea is really that we have this virtuous cycle where over time we find weaknesses in the model so that we can train the model on these weaknesses so that it gets even better and we can put it back in the loop. So we want to have like a improvement over time just through this process. And as a side effect of this process, we also get very good measurements of how good our systems really are as solutions. So to just give you an idea of the roles on the platform, again, I'm just going to show you in a minute what this actually looks like live, but just for you to conceptualize the different roles that exist on the platform, we have task owners who have constructed data sets and selected metrics which they care about. And then we have these model builders who construct models, which are then uploaded to this evaluation as a service system, so an evaluation cloud. The results of this measurement, so this is again a trusted measurement where you know that everybody, every model is evaluated in exactly the same way, using exactly the same data, using exactly the same metric. The results of this are shown on leaderboards to these model users the end consumers, the people who want to know which models they should be using for their given application. So the people who are interested in the benchmark. And then what we do with these models, we also have these breakers, as I mentioned, crowd workers, or even like linguistic experts, whoever you like. They will try to break the models, which leads to adversarial data, which can be used to improve the models. It can also be used to evaluate the model. So we have multiple rounds of test sets that are used for evaluation. And it can also be used to inform new data sets and new metrics that measure the thing we care about even better. So let me just give you a live demo of what this looks like. It's usually always the easiest way to grasp what we're talking about. So this is tinybench.org. So these are the tasks that are currently supported. So let's say we're interested in sentiment analysis. What we can do here, so we'll talk about what we see here in a bit. But what we can do is we can create examples. And in this case, so we want to find examples that fool the model, right? So let's say we want to write something negative, like this restaurant was bad. So let's make it a little bit tricky for the AI, because we have like the double A there, right? So maybe that doesn't really exist in its token vocabulary. And then we send this to the model. And so, as always with a demo, it doesn't go exactly right because it's a bit slow. But so we got a result here, and we were very successful because we actually fooled the model. So this restaurant was bad is obviously a negative sentiment example, but the model predicted positive with a pretty decent confidence. So that's not great, right? This demonstrates, I think, nicely how brittle these AI systems are actually, because there's no human who would predict positive here. But an AI system, and this is really a state-of-the-art sentiment analysis model, would predict that this is positive. So concerning. But so what happens then with all of these examples is they become a part of data sets that we use for evaluation. And so the nice innovation that we came up with to do things in a dynamic way for leaderboards is these dynaboards, or dynamic leaderboards, where we have these multiple rounds of adversarial data sets for evaluation, but also other data sets that the field might care about. So this is a non-adversarial data set that is just one of the best ways to measure sentiment analysis right now. And for all the models on all of these data sets, we measure them in a lot of different ways. So this is an accuracy-based metric. These are kind of like throughput, so raw speed. This is space, right? Memory usage. We have a fairness metric where we perturb the example and we try to measure how much it changes, similarly to robustness. So is this model robust to like small typographical errors? And then maybe you care only about different types of examples. So let's say you just care about this one data set. As you can see, the ranking here changes if you say that you care more or less. And so how exactly this is weighted is using utility functions and some core ideas from microeconomics that tell you about how you want to trade things off, the marginal rate of substitution, which I think is a very nice theoretical framework for understanding what you actually care about. And you can do the same thing, not just for the data sets, but also for the metrics. So let's say I really care about fairness and memory or something like that. As you can see, this changes the ranking, which I think is a much better way to really, as a user, select the model that you actually care about. And then we have some of these new tasks. So these are called data perf tasks, where we're actually trying to dive much deeper on the kind of data side, as Peter mentioned. So how do we get really good data sets if we fix the model and we can do whatever we want to the data set? How do we pick the new ones? So the nice thing about Dynabench is that it's a very generic solution that supports all kinds of new innovative ways of doing benchmarking and measurement. All right, so just a little bit about like how I see the broader research program then. So I think we're very interested in trying to understand what happens when we put humans and models in loops. So can we make data collection faster? Can we make better measurements? Can we avoid biases and artifacts in this process? So one of the things that happens when you have a model updating in the loop is that any biases and artifacts that it has will disappear over time, because your crowd workers who are trying to fool the model, they will find the weaknesses, they will find the biases and artifacts and give you lots of data to fix the artifacts over time. We also want to figure out what's still missing in our models, and how do we solve the next challenges, and what are they, and how can we democratize this model evaluation thing. So it's very important, even for people who don't necessarily know too much about AI, to at least understand what the limitations are of these systems. And so democratizing model evaluation, I think, is very important. So with this group of people who have been working on this, and it's really a fantastic crew of people from all over the world, and it's very welcoming if you are interested in joining. We've, along the lines of this research program, done some very nice work over the past couple of years. So we have a bunch of data set papers, so a new sentiment analysis data set, a hate speech data set, a VQA data set, another hate speech data set. So these are really kind of the state of the art for measuring things on these tasks. Then we have some evaluation papers looking more deeply at how we should evaluate models in the first place. And then we have some method papers that look specifically into what happens with this model in the loop phenomenon. So I'm not going to go into too much detail there, but I thought I would kind of, as my final point, do a little bit of a deep dive on this last paper here, because I think it shows some nice side effects of the fact that we are trying to measure models. And what actually falls out of that is also very high quality training data. So just as a reminder, this is the diagram again we talked through, but what we're doing here is we're doing many of these replacements. So in the adversarial NLI data set, we did it for 3 rounds. So 3 times where we train the model and we update it. In this case, we'll do it for 20 rounds. So it's really a long time. And we're very interested in seeing like whether this like destabilizes, or whether it has like catastrophic forgetting or some sort of like cyclical thing that we don't want, or if it actually keeps going up and gets better and better. So the starting point here is sort of the same data set that we used for adversarial NLI. And the most important thing to know is that before we did anything, we hand constructed, using linguistic experts, a test set that covers essentially all of the phenomena that we would be interested in natural language inference. So this test set really is a good measure just of NLI performance in general, according to certified experts on the topic. And so this was constructed before we did any data collection. And then once we had that, we started doing the data collection over multiple rounds, so up to 20, with the 3 different ways you can do this. So one is non-adversarial. This is just traditional data collection. So if you have more data, you get better and better. One was with a static model. So this is the same model at every step in the loop. And the green line is dynamic adversarial. So having a updated model that always updates after every round in the loop. So on the validation set, which is comprised of the data coming from these 3 different methods, you see that dynamic adversarial is better. But the real important finding is that on the test set, as I said, which was constructed beforehand, this also leads to much, much better data. So like on a data set like NLI, given that we're starting from a pre-trained model, like 5% points of difference is huge in terms of performance. So I think this is very encouraging, because while this method really just started off as a way to evaluate models in the loop and to look at the quality of solutions, the data that actually falls out of this process is also, at least from this graph, strictly better than the data that you would get if you didn't have this model in the loop. So I think as a field, we should just be moving towards having humans and models in the loop everywhere in the data collection and in the evaluation. And the main reason for that is that the data that comes out of this is just much more diverse than the static data, or so static model or no model in the loop. So what you're basically doing is you're encouraging your crowd workers to come up with very creative new ways of fooling models, which helps them get much stronger over time. And so their fooling rate goes down, they become harder and harder to fool, and this means that you need to be more and more creative, and this leads to diversity in your data, and diversity allows you to cover the space you care about much better. So the takeaway is that if dynamic adversarial data collection really gets you not only better testing, but also better training data in a faster way, why would you even do traditional static crowd working data collection? You should always have humans and models in the loop. So I think that's a pretty important insight. There's a lot of work to be done in this space still around like the naturalness of the data that comes out and how does it relate to other like machine learning concepts like active learning and continual learning. There's questions about incorporating knowledge, and can we maybe even move towards having multiple models in the loop so we don't overfit on a single model, but have an ensemble of very diverse models in the loop to get even more interesting data and still be able to measure them. So in the end, where we're trying to go, I think at least in NLP is that we want to take the next step, and so there are some people who really are riding the hype train, and I don't blame them. And I think that there is some truth to the hype that currently exists around NLP technologies, where we're pretty decent, but not great at some of the IAD problems that we've studied for a long time. And so if you don't care about the worst case, then that's fine. But I really think that we should be careful with the hype, because we're quite far from truly general language understanding in the same way that humans understand language. And of course, like lay people are going to expect that sort of language level from AI when they interact with systems. So where we should be going if we really want to claim that we understand language is this worst case. So we shouldn't be focusing on the head of the distribution and the average case, which unfortunately is something we almost automatically do if we have a maximum likelihood estimation objective in our machine learning paradigm. And we should be focusing on the tail and the worst case of the distribution. So inference is not going to match training, and we need to capture that in how we learn. So I think that really is where we should be going as a field. And luckily, I think a lot of the field is starting to take this much more seriously as well. So very finally, I'm very excited that Dynabench is now owned by ML Commons. It's a much better home for the platform than Facebook was, where this was originally developed. And we're partnering up with the amazing folks from the DataPerf effort, who wrote this very nice paper. Everyone wants to do the model work, not the data work. Data cascades in high stakes AI. So I think I'm very excited about what's going to come next with embracing the dynamicity that the Dynabench offers for really new ways of doing benchmarking on the data side and not on the model side. So I think that's very exciting, and I would encourage you to follow along if you're interested in this. And that is all I had. Thanks very much to my many collaborators on these projects. So they did most of the work. I'm just kind of telling you about it. And thank you very much for listening.